Hi everyone, and welcome to another seminar of Physics Latam. Today we have Liu Zhengwei with a two-lecture series on an introduction to Alterfold theory. He's a professor at Yale Mathematical Science Center in Zhengwei University and principal investigator at BIMSA, both in Beijing. His research interest lies in operator algebra, subfactor theory, and their connection with knot theory, lower dimensional topology, representation theory, and mathematical physics. Some of his important contributions are the development of quant language, Alterfold TQFT, Yang-Baxter relations for planar algebras, and many others. Please remember to raise your hand at any point if you have any question, and I will leave you with Liu. Please go ahead.
Hello, everyone. Thank you for joining this seminar lecture. And I will present two lectures today and Monday in the following week. And I will talk about the topological quantum field theory and the more general version, what we call Alterfold TQFT. And simply, Alterfold just means we have two colors, A and B. We have two colors in the series, and for the ordinary TQFT of McLatia, it corresponds to the B color series. And now we also have the A color in the series. This has several different motivations to study this framework. And today I will mainly talk about the motivation in the study of topological orders. And this is now very important concepts emerging from the study of TQFT and also condensed matter physics. So here we want to give a combination of the both perspective, and more importantly, we will give a understanding of the topological orders from the functional integral point of view. And that will give a mathematical characterization of these physics concepts. Before going to the abstract notions, I will actually start with a very nice example. And probably many of the audience are familiar with this example. And that's the toric code, GitHub's toric code. And the story is the topological order is a very interesting phenomenon in condensed matter physics. And the theory of their phase transition go beyond the group symmetry. So it involves the generalized symmetry. Sometimes we call it quantum symmetry inverses, and it has more precise mathematical formalism using a higher category theory. And people also call it generalized symmetry. A key point is the toric has a very explicit lattice model and a Hamiltonian, and the ground state is non-degenerate on the sphere, but it degenerates on the torus. It has a non-degenerate ground state on a sphere space. And first we will talk about two-dimensional things. It's degenerate on torus. And this is reason we call it toric code. And this has been studied also in quantum error corrections to design topological quantum error correction codes and the fault-tolerant quantum computer. More precisely, this is a lattice model. Let's say we take the square lattice. And at each edge, every edge, it's assigned as a qubit. our spin. And this will be a vector in a two-dimensional field space for every edge. And then for each vertex B, we introduce a operator for local interactions of the false spins given by the product of the poly, let's say poly Z acting on false spins. This is poly X, 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 X. And for each placket, we introduce a local placket interaction given by 4 poly Z. Sorry. This is poly X and this is poly Z. And then it's easy to check. The two operators actually commute for all vertices and plackets. So if they don't share any common part, then certainly they will commute. And the X commutes with X, Z commutes with Z. So we only need to check the case when this vertex is the corner of the placket. And in that case, we will have two pairs of poly X and poly Z. And they commute for each pair. So if we combine two together, then the scalar will be -1 squared. So that's why they commute. And those are the local commuting operators. What makes it more interesting is following. We can look at the common angle vector with angle value 1. In other words, we can take the Hamiltonian, that's the sum over all placket operator and all the vertex operator, and take the minus sign. Then the ground state. We can also normalize this so that the ground state has angle value 0. The ground space, the V, 5, are given by those vectors. And the angle value of H acting on the ground state is 0. If we consider periodic boundary condition, this is defined on torus. And then the ground state space. The dimension of the ground state space will be 4. And that's why important feature of this lattice model. But well, here it is a square lattice. We cannot put it directly on sphere. We cannot put it directly on sphere, but in general, we can check that and say if we have the triangular vertex, we can take a similar vertex operator. Or if we have a more general placket or a pentagon, we can also define a similar lattice operator. Then we can put lattice on any surfaces, like sphere. One can easily check, no matter how we write the lattice, the ground state on the ground state space, the dimension of that only depends on the topological feature of the surface. Then sphere is one-dimensional, on torus is four-dimensional, and so on. So this is really a topological phenomenon, this number 4. It only depends on the topology. Of the underlying surface. Not the underlying surface of the torus. And actually, more precisely, the number 4 corresponds to the cohomology of the torus in Z2. And this has several interesting features. Like the ground state space only depends on the torus, and from the sphere to the torus, it really goes beyond to the any local symmetry. One important feature is that take any ground state, any, well, this is given by type, depends particle. Take any ground state. It has a very important properties. So you can measure this ground state locally. Measure means that here if I have a spin, okay. And this in total, this is a vector and in a very big cubical space. And this cubical space is say C square. If we have two square populations, is this big vector. And then we can write it as a linear expansion of the 0 and 1s. And say if we take this edge, and this position may be 0 or 1, and then we can look at the coefficient of the proportion. And it's norm square. The sum of the norm square will be 1. And we can consider two values as a probability distribution. So when we look at it, measure that when we have some chance to get 0 and some chance to get 1. And the very interesting story is if we take a ground state on torus, and then we look at the local region. So we look at this local region, and then we will have 4 qubits in the region. So the reduced density matrix of phi means we just ignore the rest part, we only look at this local region. And then this will give us a density matrix on 4 qubits. The any ground state, the reduced density matrix phi is independent of the choice of phi. So you see there, the ground space is 4-dimensional. So there are many different choices. But if we only look at the local property of those ground states, then somehow we cannot distinguish them. They are locally the same. And this is a property that now people call topological quantum models. Essentially, it's something that we cannot distinguish locally, but all those ground states are in the same order. So this is a topological order. And we call it quantum because actually there are examples go beyond group theory. And also, if we consider the symmetry breaking story, it also will go beyond group symmetry. This is an important property of such topological orders. So there are many other interesting examples go beyond the p-type Torah code. Another family in 2+1 dimension. This is 2 dimension like this. It's the library model. And there, the data, hidden data, there is a unitary fusion category. So you can consider some examples like the representations of a flat group or representations of some quantum groups. Okay, at certain root of unity. There are examples like that. And then, given such categorical data, what we have is two concepts. One is the objects responding to irreducible representations. Relapse. And morphisms. There are intertidals of those some linear transformation on those representations and commuting with the group actions. And usually we represent morphism in this way. If we have irreducible representation x and y, and we can take their tensor product. So this x, y responds to tensor product. They're programmatic. And we write down such a morphism in the following way. From x times y to z, and some morphism alpha. And then using those data, we can also build a lattice, like a honeycomb lattice. So locally, we have this upper 1, upper 2, upper 3, upper 4, upper 5, upper 6, and so on. So this will define a big Hilbert space, given by the tensor product of those morphisms. And for label of lines, for this line, or edge, label of an edge is a simple object. In C. So here we can consider all possibilities. So essentially we can consider label as a direct sum of all possible simple objects. And for the morphism alpha, it's in the homomorphisms from this omega plus omega to omega. That's all possibilities. And similarly, we can define the local interactions. And one thing is that if we consider this as morphism and that's as another morphism, then on the common edge, they should share the same symbolic. So this is x, this is x, y, z. So this part, they should share the common edge. Otherwise, we consider that composition to be 0. And in addition to this constraints, there's one extra operator for each bracket. Actually, for the space in the neighborhood. And the interaction is a little bit tricky, but this can be defined using the categorical data. So we put another omega inside the bracket, and then we contract them to the boundary. So each local piece, this will be rewritten as a big sum. If locally, if you have this parallel lines, then we can do the resolution of identity. We can rewrite it as a linear sum of such terms. Okay, then we can write this as a very big linear sum of rank set, this interaction. And then one can still check, since this is interaction from this placket, if I have interaction from another placket, then obviously they are independent, so they are commutative local operators. And then one can look at the ground states in a similar way. Let's look at ground state in a similar way. Take this Hamiltonian and take the ground states. And once again, the dimension of this vector space of the ground state space only depends on the topology of the underlying surface. And there's the input category data and the input data, the input category C. And actually, there is a more explicit description of this ground state space. Like for Taurus code case, on Taurus, the dimension is 4. But here, the ground state space can also has a very explicit description. For example, on Taurus, the ground state space can be described using the following figures. Just all the morphisms in this representation category from x tensor y to y tensor x. And summing over our x and y's. So essentially, we just put the diagram on Taurus. So you can see this as a periodic boundary condition on Taurus. And this x and y has to be the irreducible simple objects. Irreducible or simple objects. And the conceptual reason is that this platinum operator, previously we put all the morphisms on the lattice, so they cannot move. But once we take the actual packet operators, then essentially that means if we take a move in the original fusion category, then it doesn't change the value in ground state space. So essentially a vector in the ground state space is somehow invariant under those local moves in the category. And if we are on Taurus, after module the local moves, then the horizontal line will be reduced to a simple object, and the vertical line will be also reduced to a simple object. And all possible morphism left is this crossing in the middle. And for the Z2 case, then you will see this is 2 times 2, and that's the dimension for Taurus code. And one can also check. This ground state also has this TQ condition. Even though they are degenerate on parts, but if you measure that locally or the reduced density matrix in a local disk are not distinguished. The ground states has this TQ condition, topological model, namely they are indistinguishable on a local disk. This is kind of the key condition to describe those topological models. But actually, it has more relations with the corresponding TQFT associated with fusion category C. Somehow the dimension of the ground state space is invariant independent of choice of lattice. And not just that, but this vector space has a canonical isomorphism with another vector space associated with the C. The given C, one can construct a topological quantum field theory. What's that? What's the topological quantum field theory? And this is a function TQFT is a function from the cobordisms, cobordism categories to the category of vector spaces. It's a monoid function. So that means for each, now let's consider the 2+1 case. That means for each two-dimensional surface, it's assigned to a vector space. So in these vectors, we always consider the finite dimensional case. So each vector space is assigned to a finite dimensional vector space. And each three-dimensional cobordism so that's a three-manifold responding. With two-dimensional boundary and a three-dimensional bound. Each cobordism corresponds to a linear transformation on the vector space. And on the left side here, if we have the union of the two surfaces, the union of two surfaces, this corresponds to the tensor product of the vector spaces for the boundary. And another map is the gluing map. So if one cobalism and the other cobalism share the same boundary with opposite orientation, we can glue them together. And this corresponds to contraction between the vector space and Abdus space. In particular, if the boundary for vector space corresponds to the surface, if they correspond to the same surface but with opposite orientation, then the vector space are linearly due to each other. And this is an axiomatization of TQFT. It's just a functor from cobalisms to vector spaces. But in other words, you can consider it in this way. You can put the vectors, vectors in the vector space inside the boundary. And you consider the string manifold as a transformation, and then you will have output vectors on the output boundary. And when you glue the manifolds, you consider manifold as linear transformations. When you glue manifolds, it just as composition of linear transformations. Now, come back to the previous examples. The empirical and level model is not only just the ground states, vector space, only depending on topology, but also the vector space has a very explicit meaning. Because the ground states are actually contributes to the TQFT. It's given this category C, and one constructs a topological quantum field theory. And this is given by Liu and Liu. Where we wrote TQFT, and we construct such a TQFT such that the ground state space will be isomorphic to the vector space in the TQFT, the TQFT space. So this is a relation between those kinetic matter physics and the topological quantum field theory. In other words, the topological quantum field theory describes the global symmetry of those lattice models. This is not just a single lattice. So somehow those cobalisms give you the transformation from one lattice model on this surface, boundary surface, to some other lattice model on the other side of the boundary surface. So somehow one can think about the categorical data, the input data for local spins, give us a local symmetry. And the theory of TQFT describes the global symmetry. And here I will give a quick description how do we construct the 2 plus 1 TQFT from the fusion category data. The fusion category is a 2D data. Somehow you can have graphical calculus on the 2D plane. And with the following crucial condition, that's the Heidegger equation. First, we can write down the vectors. Previously, we take vector in the tensor product from say x plus y to z or trivalent. We can do it one more from the three x1 plus x2 plus x3 to x5. And then by associativity, you can do it in two different ways. You can first compose x1 and x2. You can first compose x1 and x3. So it written as two different compositions. And actually, if you take the alpha and the beta, the independence as optimal basis, then after proper normalization by quantum dimension, this will give you the optimal basis of the home space, but two different choice of basis. So you can rewrite one basis as a linear sum of the other with those coefficients, and those are called F symbols or security symbols of 1+U2. So essentially, the F symbols defines a unitary transformation from one basis to another basis. And this F symbol satisfies the Fecha equation. Okay, we just have say one more object here, and then we can reduce this diagram to the other one, the other basis, but in two different ways. Okay. We first apply a move to this first part, and then to the second part. And then to the third part. On the other way, we can apply a move here. And then here, this part, since it's a tensor function, we can change the order of the two. And then get back to this. So in total, there are 5 steps. And this gives us the equation for F symbols, and that's the Fecha equation. Now, using this Fecha equation, let's see how do we construct somehow the solution of the Fecha equation. Let's see how do we construct the TKFT. The actual idea is using this. So first, we consider the 3 manifold. So if we have a boundary surface, then this corresponds to linear transformation. And if we just have a 3 manifold without boundary, then the empty manifold will just correspond to the ground field. So this is a linear transformation from ground field to ground field, so it's also scalar. So let's first see how do we give a scalar, define a scalar for this 3 manifold. Given the 3 manifold M, we can take the triangulation. the delta. And then we define the value. Okay. Define this value. Based on the triangulation. And then for each simplex in the triangulation, you can see it has those, we label all the edges by those symbol. And each face, we label each face by a morphism. In total, we have 4 different faces. We have morphism alpha, and beta, and theta, and gamma. And if we draw this still graph, so in principle, we can consider that as the inner product between alpha beta and beta gamma. And you can consider this inner product just as a coefficient here. It's from alpha beta to theta gamma. So this is the F symbol. And essentially for each tetrahedron, you can just read those morphisms and have this value F symbol of beta and theta. And then for each tetrahedron, we have such a scalar, and then we take the scalar for each simplex, we have such a scalar. And then we take the product for all simplex, for all the simplexes. And then for each edge, we can have all possible labels, labeled by those simple object X. And for each face, we can have all labels of morphisms. Note that each face is shared by 2 tetrahedron with opposite orientation. So essentially, this alpha is summing over orthogonal bases. And then on the other side, we have dual bases. So that the sum is independent of trisor bases and dual bases. With some proper normalization of the quantum dimension. Somehow the value is defined in this way in the 12-year TPFT. And the key feature is that this invariant is independent of the triangulation. So it's really a topological invariant. Value is independent of the triangulation. So it means C, this partition function is a topological invariant. And here we use the result, standard result in low dimension topology that any 2, 3, sorry, any 3, 4, there is a triangulation. And for different triangulations, they are actually just be related by so-called partial moves. For example, if you have this simplex in the triangulation, you can vote this again by adding inner vertex. Then in this way, you go from 1 simplex to form simplex, 3D simplex. And another is this one. So you can cut it by top half and bottom half, then you have two simplex. But the other way is you decompose this horizontally, just rotate that into three pieces, to three simplex. And then the standard result is that any two triangulations of the three manifolds are equivalent up to this Planck numbers. So to show this is an invariant of three manifolds, we only need to show this partition function. It's invariant under such partition moves. And for example, for this proof, on one side we'll have an F symbol in two simplices, a Salam place, and sum over all indices. On the other side, it's like this. And this is exactly the Planck equation derived from the fusion category. And you can just change the basis from one side to the other side by the unity transformation. They will also get one to the four moves. So this is kind of a proof for this triangular partition function is the invariant under the triangulation. Now, so far what we talked about the standard results in topological orders on the outside of TQFT. And this is this gives us an invariant of the three manifold without boundary. So if you want this with a boundary, then you can just do the triangulation in the box. Finally, for polygons, you can take those triangulations, this in the box. And then you run the same machine, and essentially can show, we'll define this linear transformation from boundary to boundary. It's also independent of the triangulation in the box, so somehow it's independent of triangulation. But here, on the boundary, we also need the triangulation to define this on the boundary surface. Now, this triangulation on the boundary surface, you can just consider that as lattice model we described at the beginning. The triangulation on the boundary surface just responds to the lattices. Just responds to lattice, the shape of lattices on the surface. And now in TQFT, so if we just have a boundary surface without lattice, without triangulation, then how do we describe that? And one way is to think about this just if you have a triangulation, then you have the final triangulation, you have the bigger vector space you have associated to this lattice model. If you want the torus without any triangulation, then you can consider that you have a surface, a boundary surface. This boundary surface is input and output. Now for the boundary surface, if you just want to define the vector space, like in the TKFT, associated to the surface, then you can consider that as the intersection of the surfaces with such triangulations of them. Well, in principle, so far we don't know how to take intersection of both. But on the other side, we can consider the embedding map. If you have one lattice that's finer than another lattice, then there is a way to introduce embedding map from one configuring space to another configuring space. So this can give us a limit of embedding, and then you can take the common part in the large limit, and that will give the intersection. So this is one way to define those configurations on the boundary surface without any triangulation. And there is interesting check. The ground state, the vector space defined in this way is the same as the ground state space. Of the Hamiltonian given at the beginning. So this is the previous way to identify the ground state space and the corresponding vector space in 12-0 TQFT. Now we will give another perspective to do this stuff using our Alterfold TQFT. Okay, yeah, now let's continue and discuss our approach to the results we measured just a while ago. So how do we reproduce those like results, conceptually or in some more natural way in the output of TQFT, and also the input data. So what's the input data? So previously, our input data is the unitary fusion category C. Now, we will consider this data in a different way. We do not take this as input data. What we need is a graphical computation function. Of this real function. Let's see on the 2D lattice models. So what's that? You can consider the 2D lattice model in this way, and locally, let's write down the memory model because you have a local space. Okay. Previously, the level model is in the category C. There are morphisms of in C. And also for lattice shape, it doesn't have to be the honeycomb lattice on torus. It can be more general shape. And the partition function of the map from this to a scalar. So what's that map? If this is a configuration on a sphere, since this fusion category, unitary fusion category is always spherical, so we can do any isotopy we want on sphere, and then we can evaluate. You can just evaluate these morphisms in the fusion category. Just like the tetrahedron case, we have 4 morphisms in tetrahedron, and then we can evaluate that to the F symbol. Here, just in general, we can evaluate this diagram to a scalar in C. So this will has the following properties, that this evaluated map is invariant and isotopic. And on the sphere, isotopy and homotopy are the same. So we don't distinguish them. So it's a evaluated map, it's invariant under such isotopy on sphere. And secondly, since this is a unitary fusion category, this evaluated map has reflection positivity. And that means if we have a configuration, the X on the left side of the lattice, and its mirror image on the other side of the lattice, theta X. And then when we compose them, the scalar, the final value will be bigger or equal to 0. This is some basic version of the reflex positivity, corresponding to the unitary condition of the fusion category. And here, X doesn't have to be a configuration on one lattice. The X can be even the superposition for different lattices. Know that once they have the same boundary, then we can glue them together. But inside this disk, the lattice doesn't have to be the same. They can be different. And then on the superposition of such configuration space, it has this reflex positivity. Now, on this side, you can just take these two conditions. Let's say in the partition function on the 2D lattice model means lattice model here means for each local part. Okay, so this is maybe trivalent vertex or four-valent vertex. So for each local shape, it's assigned to a vector space. For each local shape, maybe like trivalent or four-valent or gathering. But each such local shape is assigned to a vector space. Vector space of the local space. And then the lattice model given a general lattice, the configuration space will be just the tensor product of those vector spaces. And since now we are going to consider reflection positivity here, we further require vector space to be Hilbert space, so that when we take a reflection, we will have a due induced by the inner product. And then for partition function on those lattice models, just for the local shape, we consider all possible lattices with such local shape. And we put everything, we put the lattice again on the sphere. Now we define partition function for every such lattice supported on the sphere. Given a partition function on the sphere for all possible lattices on the sphere such that so this partition function C is the first condition, invariant and isotopic. So that essentially means we don't really care of like the distance of lattice, but only the combinatorial shape of the lattice. And this also involves like translation invariance. And secondly, is this reflecting positivity. The reflecting positivity really just means this. We have a lattice, right? And since each local space is not just vector space, but Hilbert space, so there is a well-defined evolution on the local space. And then we can define x and cx in this way, and then take its value and require this positivity holds, reflect positivity holds. That's the second condition. And third condition is certain lattice. We will explain what this lattice very soon. But essentially, say that the vector space corresponding to all those local space first has to be finite dimensional. And using this reflecting positivity, this you can consider that it defines an inner product for the vector space with boundary, for the vector space on disk with boundary. So somehow we require the inner product induce a finite dimensional vector space from its quotient. And that kind of finite space. And the main theorem is that given such a partition function on the lattices, then we'll obtain 2+1 unitary TKFT. And actually, we will obtain the square root TKFT we just described. And in addition to that, we will obtain this Alterfold TKFT. And that means the TKFT will have AB color for the box ring manifold, two different colors. And in the variability TKFT, the manifold will be corresponding to the B color part in the series. Now, first, let's describe how do we obtain a 2+1 series from the 2D series. Step one. Essentially, we start with a 2D lattice. We can just consider this as a string net, those kind of graphs on the sphere. We have partition function that's the sign value of such graph to a scaling ground state space. Now you can consider this is a graph with those string nets on the field. with those local spins. So the initial data is the map from those data to a scalar. That's the initial data. Now we impose one additional color. We consider bulk color as B color. Because inside the sphere, the 3D ball as B color. And the outside color is brown color. But so far, let's ignore the A color part and focus on the B color part. The inside part is B color. And then what we have is for any 3 disk, 3-dimensional disk, not 2D, 3-dimensional disk. And its boundary is the 2D sphere. And then inside the 2D sphere, it contains those lattices of spinets. So given such data, we map that to a scalar C. And then let's see what we have from the reflection positivity. We can have half of them. So say the vector side half. You have those spinets on the vector side. On the half disk, and the boundary will be half sphere. And the right side. Once they share a common boundary, then you will have a vector space V with positive orientation and another vector space with negative orientation. Okay, just with this boundary. And the lattice inside could be any possible shape. So essentially, this is a very big vector space, since here we are taking all possible shape of lattice, and each one is a tensor product of the local Hilbert space. So this is a big DXR. You can consider this as a kind of higher dimensional analog of the Fock space. You just take all possible tensors and take DXR. But different from Fock space, it's just the abstract tensor. Here, the tensor product also captures the local shape of the lattice. And then reflecting positivity essentially is a map from this vector space to the ground field. Okay, this is a linear map. Or you can consider this as an inner product that induce an inner product. Between this vector space and itself. Because the right side will be the mirror image, so that's a dual space. This induces the inner product. And reflecting positivity means this is positive semi-definite. And then we can take the kernel, namely those vectors who have zero inner product with any other vectors. So we can define this Gaussian space as dimensional vector space. Dimensional vector space modular the kernel. Let me see B without the. But even though this dimensional vector space is very big, this vector space is big. But modular the kernel, this vector space might be very small. So what we are really interested in is this Gaussian vector space. In particular, since when we take as topic, it doesn't change the particular function. So any S topic gives the equivalence relation in this vector space. So that means if we consider vector in the Gaussian space, everything is well defined modular S topic. But not only modular those S topic, it also modular additional relation from the kernel of the partition function. For example, in the language model, this kernel will involve those local moves, the F moves, defined by the F symbol. So after modular this kernel, this vector space could be very small, and in general, it is very small. And there is a conceptual interpretation of this reflecting positivity framework in constructive quantum field theory. It's just saying that we are considering this the theory on the left side. You can consider the mirror as the time equal to 0 space, just the current world, and the left side will be the past, and the right side is somehow the future. And then this Gaussian space from everything in the past, we are actually integrating them to the current time. And this is another way to define passive integral. So this vector space is actually just the physical space. And defining the physical space by taking caution by this reflecting positive functional integral plays the role of passive. This is the machine to define passive integral rigorously. So this is the way to formulate passive integral. From the functional integral point of view. Even though this is a discrete version. In our original quantum field theory, that's a continuum version. Here it's discrete. And actually, for discrete version, there is one advantage that this vector space could be finite dimensional. And indeed, it is like in the LV model case, in many interesting cases related to TQFT. So this finiteness will involve this condition that this Gaussian space is finite dimension. That's a requirement of the finiteness condition. In principle, this is not necessary for physics interests, but for the mathematical formulation to be rigorous, to ensure the partition function later we'll see is a finite state sum, we need to require certain finiteness condition.
Can I ask a question?
Yeah, sure.
So this is the same to obtain the Turev Piro TQFT, or is there any difference?
We will see the B cover theory will be exactly the 12 0 if the input partition function is the evaluation map of the fusion category.
Okay.
So in general, the theory will involve the A color part, and in general, the partition function doesn't have to be from a fusion category. So by the end, we will show how to construct such a partition function without knowing any categorical data. So this will be a machine to construct TQFT or topological orders just without knowing the category symmetry. That's the main thing we will see by the end.
Okay. And another question is, like you mentioned, is this defined to all dimensions or so far to 3 dimensions?
Yes. This works in all dimensions, not just 2+1. But it's just easy to explain 2+1 literature. So most people are familiar with that. And also it's easy to draw a picture for 2+1 case. Actually, some results are even non-trivial for 1+1, but most results are more interesting in the 2+1 case.
Okay.
So this is the input data we have. This is the partition function and reflecting positivity with certain finiteness condition. Now let's see just from the data, how do we build a TQFT from such data? So what we have at this currently is a particular function from, let's say what we have is now is a particular function, to step one, a particular function from the 3D disk. Its boundary is the two sphere, and that contains some data. Let's say gamma, that's the spinnet, and left is the scalar. This is the spinnet. Or in general, this will be the configuration space of the vector in the configuration space. Okay, and then in the second step, from the reflection positivity, we obtained this vector space. Given by the orbital one with boundary, modulo the kernel of the partition function, which induces positive semi-definite in the product. And the third condition require that this to be dimensional. Now let's see how do we extend this partition function. This from the 3 disk with defects on boundary or configurations on boundary. How do we extend this from the 3D disk to a general 3 manifold with a boundary surface and defects inside it? How we extend this partition function. So a general 3 manifold, and its boundary will be a 2D surface. This is not this is just surface, not S2. Let me see, use notation. On this space boundary. The first step is we can take the unit of 3D disk. For a single one, for single ball, we have this value. Now for this kind of unit, we define the value multiplicatively. This is a multiplicative structure. Structure of the partition function. Somehow I consider that as a higher dimensional analog of quantization. Now, from this one, from vector space, we can impose this relation that if you have a similar this one, there may be a boundary condition here, the same boundary condition. So we may have vacuum cylinder partial cross interval. So if there are say boundary points on the boundary disk, when we take the vacuum cylinder, we also need to product that boundary condition in this way. So essentially, if you consider this as a linear map in TQFT, this will be the identity map on this boundary vector space. And then we impose the following relation. And this will be given by linear sum of x in the orthogonal basis of the vector space V for this given boundary condition. And it's actually V tilde. After we take quotient, this V tilde is a finite dimensional vector space. So we induce this relation. And certainly we need to show this relation is well defined in the following sense. If we add two hemisphere on both sides, okay, there's three pieces, then this will be a ball. And the partition function will be defined as given by input data. And on the right side, we will have a function like this. This is x, q, something like this. On the right side, there will be two balls. And then the two balls, the partition function is defined multiplicatively, as we mentioned in the previous step. So essentially, we need to show they are the same. And this is easy to check that actually we do it reversely. That means if we have those partition function, if we extend it multiplicatively, then we cannot distinguish this diagram and that diagram from the partition function. Okay. So we cannot distinguish them. So this becomes a local move. This is in the kernel of the partition function after we extend that linearly. So we can use this move when we compute the partition function of multiple balls. Now the third step, after we have this relation, then we can define partition function beyond multiple balls. If we have a torus, if we have this torus, again, it's a solid torus with B color inside, a solid torus. Then we can apply this previous relation. We can cut it in this way. This will be sum of the x label. I just ignore that. So once we cut it, then this becomes a ball. So partition function is well defined. So we can define the value of torus in this way. And then again, it's non-trivial to see this as independent of the place we cut it. Okay, we cut it here, we can also cut it here, or maybe even both. And we need to show they eventually contributes to the same value. But in principle, just once we have this relation, then actually we can extend the partition function, not just to the three manifold given by the union of balls, but also we may have those kind of torus. And conceptually, you can think about this as a one handle. This is one dimensional handle. So if we have a one handle in three manifold, then we can cut it this way. Now, once we have this value, then we can run a similar machine like this. We can cut torus in another direction. This, how do I draw this? to see in this direction, the parallel to the black ball. So we can cut torus into two pieces. So we will have some configurations of spinels inside torus. And we want to rewrite this as so this is, we have B color inside. So you can impose this additional relation. And it satisfies the following relations. So that, similar to that part, we can compute its inner product in two different ways. Just by gluing the torus outside. And on one side, we will obtain a ball. On the other side, we will obtain this torus. So we glue this boundary. We glue the boundary. Then this will be a ball, a three-dimensional ball with B color inside. And this part will have a hole in the middle. And this will be a torus. And then we can define the value of torus using the previous one. And essentially, once we have the value of torus, then this will again induce a unique relation such that their inner product unique relation such that the inner product is contributes to the same value for the partition function. Or in other words, this is a linear relation that cannot be detected by the partition function. And this is the relation we consider this boundary as a two-dimensional disk, multiply the interval as a one-dimensional interval. And we consider this as a mapping cylinder for a small neighborhood. And this will be considered as a one-dimensional line across a two-dimensional disk in a small interval. So we consider this 2D disk. This is the direction for the composition. That's just a 1D multiplication. This will be the 2D multiplication. And on the right side, the right side will be given by three 3D balls with 2 of them. That's B0, S0. 2 points. And this one, the right side will be the 2-dimensional disk multiply the S1, that's a solid torus. And once again, we can repeat this process and get the last relation. D0 multiply this three manifold, it changed to D1 multiplies 2. And pictorially, that's just the B3 manifolds. Okay. With the boundaries of field without equation. And this is written as the linear sum of again its manifolds with B covered outside and A covered inside. Or somehow empty diagram inside, and these equations on this boundary surface between A and B. And if you look at the B color part, it will be this B1 multiplied S2. Okay. The small interval multiplied the sphere S2. And again, this will satisfy the relation such that if you take its inner product with the due, and on one side you will get this 3 ball, on the other side you will get yeah, on the other side you will get this D1 cos S2, and then that value can be defined using previous partition function. Just by repeating this process. So essentially the key point is the following. We want to introduce those relations as following one principle. And we start the partition function z step by step. And then we can always find one additional relation that cannot detect the difference of partition function. So the kernel of the partition function will induce the additional relation. Then we just repeat this, the steps. And then we will have this relation. The first one is we evaluate D3 from D3 to a scalar. And the second one is from D2 cross D1 to this D3 cross I0. And this is the third one and the last one. So we have 4 relations. And one main result is that those 4 relations derived from the kernel of the partition function are consistent. And consistent means any namely for any 3 manifold M3 whose boundary is a 2D surface, and that contains those lattice models on the boundary surface. For any such data, its partition function Z is well defined. And this is well defined modulo those relations. So for any 3 manifold, first we need to show how we define the partition function. Now the moves for any 3 manifolds the sketch of the proof. So any three manifold, we take a triangulation. Okay. And then how do we apply the smooths? So for each vertices, for every vertex, we apply this last relation. Because for every vertex in the three manifold, we take its neighborhood, it will be a three-dimensional disk. And then we can apply the last relation. We can remove the three-dimensional disk in a small neighborhood. And essentially, we dig out the inside part. We remove the neighborhood of this vertex so that it changes from big part to big part. And then for every vertex, really just means the zero index of the triangulation. And for every one simplex, then we apply the previous move. This is one simplex D1, and a small neighborhood. Multiply D2. Okay. This is one simplex and a small neighborhood D2. And then we remove that. So inside, in the middle, this will be, let's see, this will be B comma here, and inside this terminal, that's A comma. So in this way, you can remove the neighborhood of the one simplex. And then for the neighborhood of two simplex, we apply this. And then the neighborhood of three simplex, or just the three simplex itself, we can remove the three simplex to scale. So this is the evaluation map based on the triangulation. Okay. And this is really similar to the evaluation process of the 12-year TKFT. And slightly different difference is that here on the three manifolds, we have those boundary decorations. And the boundary decorations is defined up to S topic. So we don't need to take triangulations on the boundary to define the partition function. There's no requirement of triangulation on the boundary of the three manifold. But in other words, when we define 12-0 with boundary defects, somehow this is still well defined multi-local moves on boundary. So this tells how do we define partition function or general three manifold with boundary surface. And now here we need to make it more explicit. And we call this boundary surface the space boundary that we have decoration. In the ordinary TKFT, it's the time boundary. On time boundary, we don't have decoration in the box. It's just a manifold. In TKFT, we have polygons. This is three manifold. This is time direction. This part will be the time boundary in the usual TKFT. And here we may have a space boundary. Even with the decorations, this effects. And we call that our lattice models on the space boundary. And then you can do it similarly, just you can compose time boundary and also compose the space boundary. And on the space boundary, everything is well defined how to isotopic. Essentially, it's not trivial to prove that those relations are consistent, just like for the 12-0 case. If we want to show the partition function is independent of the triangulation, we need to show it's invariant under the partition move. And here is a similar story, but we have some improvement of this proof. We don't show it's invariant under those partition move. Instead, we show it's invariant under more elementary operation. So we prove that Z is invariant under the so-called half move. What's the meaning of that? That means in the triangulation, like we have simplex. Half move means we can cut the simplex, like the three simplex, into two pieces. Okay, that's a move. We can also cut the two simplex into two of them. One simplex into two of them. And this is half move. And the key point is that first, any triangulation and two different triangulation of a three manifold, they are equivalent under such half moves. And this is actually very easy to show because the usual triangulation or subdivision are combinations of such kind of half moves. And secondly, when we derive those relations in the previous steps, so when we derive those relations, we use this inner product. And the partition function is invariant under those inner product. And that condition is exactly those half moves. So those half moves are exactly those relations when we build them from the kernel of the partition function. So somehow this gives a more elementary ingredient of those moves. So you can derive the previous like subdivision moves from the small elementary ones. And they are here in this report, they are just built from the kernel of the partition function. So it's consistent with our framework. We derive the relations. So it's much easier to prove the consistency in this way. And as a quick consequence of this idea is that this method really works in any dimension. Since when we derived that, we didn't really use the dimensions. You can see the formula consistency to any dimension. And the ideas are just the same in this way. It's dimension independent. The proof is dimension independent. Well, that's the key point. And another technical thing is when we define the TKFT using those data, we need to require any relation is a finite sum. Otherwise, this final partition function will be infinite sum. So the convergence will be a problem. So to avoid this technical difficulty, we assume all the linear sum will be finite sum. That means the induced vector space, the Cauchy space, for any given boundary condition will be finite dimensional. Not just the disk, but not just the boundary circle, but more general boundary conditions. And that's the finiteness condition. On the categorical level, that really means not just every home space is finite dimensional, but number of simple objects is also finite. So this is the main point, that the key point, that is once we have this reflection positive particle function, then we can derive all the relations just from one principle, that the kernel, if the kernel of the partition function, if the partition function doesn't detect the difference of the diagrams of graphical calculus, then we have this relation in the kernel, and then we just impose this relation. Just this principle, then we can derive everything we want. Next time we will explain this A-color theory. So this is really saying that we are defining partition function based on triangulation of the B-color manifold. We can ignore the A-color part, and that A-color part will correspond to the surgery theory in the restrictive interval TKFT. So we explain more about that next time. And now, just based on this partition function, we can easily explain those concepts in the previous lattice models. Like for Alterfold, general level model, let's write level model. For level model, so this is the original configurations, and on each local part, we have those local spins. This is tensor product. Then what happens to the action of the Hamiltonian on this vector space? The original configuration space, if we draw this boundary condition, is this. On the boundary surface, we actually have this B color inside. There's B color in this three manifold, but on the boundary, it induced to a B color on two manifold. And with A color in those holes. So it is AB color TKFT, what we call Alterfold TKFT, because it has alternating colors. Then we can build the original lattice model just directly using those AB color boundary. So if you have a boundary condition like this, and say if this is a simple object X, then that means on the dual part here, you will have this object X. Or in general, if you have all possibilities, this will be the omega color. Okay, unbounded. Okay, those pink lines will be the boundary condition. And this vector space is the tensor product of the local space. And that's the original configuration space. Of the lattice model. And you can even change the shape of the lattice of this white lattice. And then you just blow it up. You look at neighborhood, you have this corresponding B color region. It's just neighborhood of the lattice. And then the Hamiltonian. H is given by the sum of those bracket operators. And those bracket operators are given by this action on the cylinder. And there's a very nice relation that if you have this hole, we call it hole, and I have this BP operator given by action of what we color, Then you can kill it. You can just fill this, remove the hole. And in the 3D case, the relation is like the following. This is A2. And this is the main color or cubic color. B outside. Yeah, just this relation. The small color could be moved. But here we are describing this move using the 80 colored manifolds. And previously we read the relation from the right side is linear sum of the left. And for the Levy model case, the relation induced by the kernel of the Poynting function will be just this move. And then once we have that, then the sum of all those BP operator will just kill all the holes. So essentially, the ground state space will be just isomorphic to the vector space without holes, without A color part. Then everything is B color. Just the boundary is always B color. So if it's torus, then it's just a purely B color torus. And then in our TKFT, if the boundary is purely B color, it's exactly the original vector space in the 12-0 TKFT. So a quick comment is just that what's the meaning of taking the ground state of Hamiltonian? This bracket operator just kills the A color holes on the surface, on the surface. So essentially, if you have such hole, then the configuration cannot move freely on the lattice. But without hole, then the configuration can move freely on the lattice. So after you kill all the holes, then everything will be well defined, just modular isotopics and local relations. So this will be another approach to derive all the selective models, and also derive this ground state is coincides with TQFT. And also we can use this proof to show all the ground state has topological orders. That means they are locally indistinguishable. And the point is just the following: if we have this local lattice and some ground states, and if we want to compute the reduced density matrix, that means we glue this. That means we just glue all the, we take partial trace of all the rest parts of the ground states. So this is the rest part. You just take partial trace of the rest part. And then graphically, we can also give a representation of such ground state, say on torus. We just take the same lattice and we consider those as an output disk that you can have the local space as output. And this configuration will just produce a ground state. And if we are on torus, then we can write down all the ground states as a map. So you have a torus outside, it's t squared plus 1, and the torus inside is t plus 0. And you have this lattice on this top piece. Okay, this represents a non-trivial ground state. And the inside is part, in the middle, this is called B color. And inside, the lower half piece will have all possible configurations. But here, there's no constraints. So you can take the configuration model of all the cones. And that's what we mentioned at the beginning. For the ground state space, they are described by those stringless model local moves. And the outside part will be the ground states in this big tensor product, the condensed matter ground states. And this is just the encoding map. Now for quantum computing, the underlying t squared times 0 is called logical qubits. And this is how you encode logical qubits and physical qubits. And topological algebra means you just take a local piece, measure a local piece, and you cannot distinguish them. And the interesting part is, if you just take the reduced density metric of local piece, then essentially you eliminate all the t squared times 0, no matter what's inside. Just by the moves, it's easy to show. This local piece, density metric, you can write it down explicitly. Just this configuration times is still. Just include this diagram as a still and consider that as density matrix. So actually, we not only know it's locally indistinguishable. In this framework, we can write down explicitly what's this reduced density matrix, local reduced density matrix. And also, this argument again works for all dimensions. So that means once we have this reflecting positive, and as the top being invariant, Arcane function, and with certain finiteness, complete finite Arcane function. Then this is on the n-dimensional, n-2 n-dimensional matrix models. So plotted on as n. That's the theory. Then what we obtain is a n plus 1 unitary Alterfold ICTP. So that have both A and B color. And actually, this not only involves TKT, the local symmetry will be given by a unitary n category from Alterfold completion. The local symmetry, and from the higher dimension bulk, we can also have its field some called higher center or deeper center. And the relevant concepts. And the ground state space and the canonical Hamiltonian. H. The Hamiltonian is just given by those omega colors, but in all codimensions, not just the top dimensions, in all dimensions, so that we can kill the whole in all dimensions. And such that it's ground state. It's ground state space. It's the same as the TKFT space. But here in our case, it's the TKFT B color space. Because if the manifold is purely B color. So some of all the results we mentioned for the 2 plus 1 case for YW model will work in this case. And those ground states has topological quantum orders. So they are locally indistinguishable. So this is a machine to construct such partition function. That's reflecting positive and S-stopping environment to construct TQFT and higher category TQ topological quantum orders. Just working in all dimensions. And actually, even the definition of unitary N category is non-trivial. And here we propose a definition that's from this framework. And from this point of view, the last remark is there are many examples. Many highly non-trivial examples. One can think about it in the following way. From the paradigm of matrix, matrix product. Operators. What kind of momentum it is? Just the conceptual reason is the following: how to construct such a partition function. It seems difficult as well because we have those conditions that reflect positivity and S-stopping environment. That's how to construct them. And actually, there's a machine. For S-stopping environment, it's easy to understand. You just construct the partition function. Let's say just for the one-dimensional case. You have those local spins, and they want to construct a partition function on that. They can take this so-called paths. Locally, they are the same. And just glue the tensor together. And then you can glue those tensor product to these paths. And this will define the partition function. They are input, this is linear function. And this partition function is S-stopping inverse. Namely, once they are locally the same, you have S-stopping inverse. And reflection positivity means if you have some x here, and you have theta x here, then this should be reflecting positive. And then for all those parts, that just means if this is the mirror image of that for local term, then you have those conditions. So if those parametric product state given by those kind of local operators like this, okay, or in the two-dimensional lattice case, you can have a local operator like this, with higher paths. Then the first two conditions are always satisfied. And another thing is that if you consider this partition function as the ground state of certain Hamiltonian of local interaction, the reflecting positivity of Hamiltonian can be checked easily using machine, the Lindblad criterion. That's also a crucial condition in the constructive quantum field theory. So somehow it's very hard to build a highly non-trivial N category directly, in particular unitary one. But in this case, we can use the lattice model, one-dimensional higher lattice model in box, or the corresponding Hamiltonian. And then we can really prove the first two conditions. And the third one, the finiteness condition is more technical. Somehow much more technical. So conceptually, this framework gives a characterization of such kind of topological orders corresponding to TQFT with a boundary theory for some unitary N category, and the box theory gives this TQFT, and a complete characterization of such topological orders without knowing the categorical symmetry in advance or in prior. So the category symmetry in this case will be emergent. So those parts are emergent. Okay, so this is the question that's asked by ICTP and Salam for a long time, just to study those topological orders. One way is using symmetry, like general symmetry, and the other way is using Hamiltonian or ground state space. How to characterize that? And the answer is okay. We just take the reflected positivity, and then that's the answer. Thank you.